Okay, 7.8 is about certain types of differential equations, specifically ones that have that are differential equations for exponential models. So these are ones that show up frequently, and we are going to look at first how to write them and then some interpretation stuff. So first, if we are given a statement of proportionality that says something like the rate of change of, a population of geese, or a population of a town, or a population or an amount of bacteria or something like that is proportional to a current amount, then we end up with a differential equation that looks something like this. I am going to use dy over dt because frequently this is time, so that's why I'm specifying the t here. And it's going to be equal to k times y. So what does this mean? This is when we have a statement, once again, that says the rate of change of an amount of whatever population, geese, I don't know, is proportional to the current amount. Okay, so the rate of change of an amount is proportional to the current amount. So y is our amount, our population, whatever. We also know that proportional is a direct variation relationship, which we talked about being y equals kx, but in this case our y is the derivative and our k times and our amount is, or our input variable then, is the x. So if we have this type of differential equation given, or this type of statement, this is our interpretation. And this is a model of exponential growth or decay. Very quickly, I'm going to go through the solving of this. Let's do this over here on the left. I can probably fit it in here. Just so that we kind of see how we get from one to the other, meaning you should be able to solve that on your own. But you could also just jump to knowing what this looks like, okay? So if I am solving this differential equation, I'm going to multiply by dt and divide by y to get rid of that and that. So I have 1 over y dy equals k times dt. And then I can integrate both sides. So I have natural log absolute value of y equals kt plus c. I can take the exponential of both sides, and I'm going to take the absolute value bars off because in all of these situations, y is not going to be negative because we're talking about a population of something. I can't have a negative number of people or geese or bacteria or something like that unless maybe we talk about negative population being zombies or something, but there's absolute value bars around it. So I'm going to say zombies can't be real because of this. So you're welcome, world. Anyway, we have y equals e to the kt plus c, which is also e to the kt times e to the c, which is also, doing one more algebra step, e 2.7 to any constant is still a constant, so that's just another c, and I'm going to move that to the front. So c e to the kt. Okay, this should look a little bit familiar. This form you saw in Algebra 2, and probably get in pre-calc, is the same thing as saying y equals, leave space for a second, e to the kt, or maybe even you saw it with an r in there. And maybe you remember that this coefficient might be p. If you remember y equals p times e to the rt. Okay, do you remember seeing this? This PERT formula, this is continually compounded interest or exponential growth. The reason I'm leaving this blank is let's specify if my time is 0, so in other words, I'm going to get rid of this, at my time 0, at my starting point or initial time, if this is 0, this is a 1, meaning y is the same as my population at time 0. So this is a little bit more specific than just saying c, where y sub 0 is my initial population, and k is my rate, and then t is the time. Okay, so an initial population is when t equals 0. Okay, one thing I want to add here is that growth, this happens when k is positive, and decay happens when k is negative. Okay, and our our direct variation relationship of a rate of change of an amount being proportional to the current amount will always be of this form, meaning we don't have to redo all of this calculus to solve if we know that we have exponential growth, okay? Which we do, or law of growth, law of decay, if you remember hearing it called that. All right, so let's do some examples. With this one, we have a kitten weighs 85 grams at birth. That right there is telling me that this is T sub 0 at birth at time 0. A weight is, let's see, W for weight. So weight sub 0 is 85. Okay, during the first 4 weeks after birth, its weight in grams is given by the function W, which satisfies the differential equations dW over dt equals K times W. T is in days, K is some positive. Okay, so right off the bat, let's move this over. Right off the bat, I know from this differential equation that I must have an exponential growth function. So I know that the weight of the kitten is equal to the initial weight times e to the kt. Okay, now, could I go through and solve that to get there? I sure can, but it's faster for me to just recognize that is a law of growth function. So now, what do we know? We need to know what k is, and the initial weight we said was 85. Well, right off the bat, I'm already thinking C. A is kind of exponential growth, but it's got this plus 81. B is linear. C looks the way we want it to. And D is a quadratic, which is not what models the situation. So C is going to be my correct answer, but just to double check here, I can plug 85 in for the weight at birth, and e to the, and the other thing I can think about is that k is a positive constant. That matches there because weight should be increasing. So yeah, I should have W equals 85 e to the some number times t. So my answer is C. Okay, so I'm not solving anything here. I'm just recognizing that's a law of growth problem, and I'm plugging that in. Okay, number two. The rate at which the drug leaves the bloodstream is proportional to the amount in the bloodstream. Okay, so the rate that it's leaving is proportional to the amount. Again, that's telling me it's a law of growth. My differential equation, I'm going to use, let's see, A for the amount, so the rate of change over time of the amount in the bloodstream is equal to K times A. All right, which also is going to be an A of T equals A sub 0 e to the KT situation, but let's go ahead and figure out what those pieces are. Apologies if you can hear Mr. Morrissey yelling in the hallway. Okay, so what do we know? 400 milligrams is administered, so this is the initial amount. This is our A sub 0. Okay, so A of T is equal to 400 e to the KT. I know that. I also am given after 2 hours, approximately 376.7 milligrams remain. Let's plug that in for A of T and for T, and we can use that to solve for K. This is calculator active. So A of 2 is equal to 400 e to the K times 2. So, let's see, A of 2 is 376.7. Okay, so then I need to divide both sides by 400. And then take the natural log of both sides and then divide by 2. So K is equal to 1/2 natural log of 6.7 over 400, which on a calculator is approximately negative 0.030. All right, so then what am I looking for? My equation for A of T. So A of T equals initial amount of 400 milligrams times e to the negative 0.030 t. All right, there's my function. Okay, next example. Let's see, we've got 4. Okay. Population P grows according to a differential equation dP over dt equals K times P. So once again, I already know that I have a law of growth problem, and I don't have to do the calculus to solve to get that. All right, so I can write that, let's see, the population at time t is equal to the initial population times e to the kt. All right, if the population of the city doubles every 12 years, what's the value of k? Well, I don't know the value of my population at any time, but I do know that I can set, if I say my initial amount is 1, I can set my later amount as 2, and I'm going to have the same ratio no matter what. If the population started at 500, then this is 1,000, and the first thing I would do would divide both sides by by 500 to get 2. Or, if I start at 7 million and 14 million, once again, I would divide first and get a 2. So I'm going to use a ratio. So 2 is equal to 1 times e to the k times 12. Okay, so then taking the natural log of both sides, and then natural log will get rid of the e. So k is approximately natural log of 2 divided by 12, which, actually k is exactly that, but then that is approximately 0.05776. Okay, so then, now it doesn't ask me for an equation yet, but I'm going to use one down here. So it says, in how many years will the population triple? So I'm going to use my initial population still, I'll keep that a 1, and set my after population as 3, and I'm solving for t. So e to the 0.05776 times t. I know that you know this already, but we don't want to round anything until the very end. So when I'm typing this in on my calculator, I'm retrieving the 0.05776 that I got from my natural log 2 divided by 12. I'm not retyping that as a decimal. All right, so then t comes out to be the natural log of 3 divided by the 0.05776, which is approximately 19.020 years. Did I answer the question? Yes. In how many years? 19.020. It doesn't tell me to round to the nearest year, so I'm just going to leave it like that. It doesn't say this is, where time is years after 1992, and now I need to add 19 years to figure out what year. It just says how many years, so I'm done. Okay. Last one is a little bit algebra heavy. So it's going to take some time, and apologies if there's not enough space on here. As I was making a key, it got quite a bit bigger than I anticipated. So sorry about that, but stick with it. Okay, and we are going to use a calculator for part of this, but I will be writing things out by hand. Okay, so the fish is represented by F, are being introduced into a man-made lake. The rate of change of fish with respect to time is directly proportional to 900 minus F, and T is measured in years. So this is a differential equation situation because I'm talking about a rate of change of fish over time, and it is a direct variation, but it's not K times F, it's K times 900 minus F. Okay? It's a little bit bigger. K times 900 minus F. So I am going to go through the process of solving this by hand because it doesn't quite match the law of growth, but it is exponential. All right, so I'm going to multiply both sides by dt, and I'm going to divide by this whole quantity 900 minus F on both sides. So I get 1 over 900 minus F df equals K times dt. And then I'm going to integrate both sides. And this looks like natural log of 900 minus F. However, I would need to consider a composition. So like U substitution, my du needs a -1. So put a -1 on the inside, negative on the outside. So this is negative natural log of 900 minus F equals KT plus a constant. All right. And then from here, we do, like we talked about in 7.6 and 7, for a particular solution, we do want to plug in ordered pairs early to solve for C. And so I am going to start doing that. I actually have 2 ordered pairs. I know that at time 0, we have 400 fish, and at time 3, we have 600 fish. I am going to move the negative over here just to make that a little bit easier. So I feel like I'm going to forget it if it's over there. So I'm going to move that to here. Okay, let's plug in 0, 400. And so we have natural log of 900 minus 400 is 500. I don't need absolute value bars, that's positive, equals negative k times 0 plus c. So that means that c is natural log 500, and that negative didn't matter. Okay, so back to my equation, natural log of 900 minus f equals negative kt plus natural log 500. And now I still have another variable that I need to solve for, and that's the k. So I'm going to solve for k using the ordered pair 3, 600. Let's do that in this color. So natural log of plugging 600 into here gives me a 300 equals negative k times 3 plus natural log of 500. I'm going to subtract natural log of 500 and divide by negative 3. Now, algebra, natural log of 300 minus natural log of 500 is, I'll do it in 2 steps here, is natural log of 300 over 500, which reduces to 3 over 5. Okay, so I subtracted this from both sides. Don't get hung up on the algebra. But then natural log minus natural log I can combine, and 300 over 500 I reduce to 3/5. Okay, then I'm dividing by negative 3. So I get that k is equal to natural log of 5/3 over 3. Where did my negative go? Well, having a negative here, I can move that up to as a -1, and then it becomes an exponent. And so I didn't want to deal with negatives, so I just wrote it like that. Okay, that is a little bit messy. Let's go ahead and find the decimal for that. The decimal for that is -0.170 approximately. Sorry, correction, positive 0.170. Okay, and I'm keeping that number on my calculator, but plugging this in is going to be a lot easier, so I'm going to write it with the 0.170. Okay, so plugging that back into, just in case, plugging that back into this line right here, I have natural log of 900 minus f is equal to negative 0.170t plus natural log 500. Okay, and then now that I have my value for k and my constant, I need to find my particular solution by solving for f, because it does say to write and solve the differential equation that describes the situation. And I only have one f, so I do need to isolate it. I'm going to take the exponential of both sides. Okay, so I'm going to have e to this whole quantity over here, and then but e to the natural log will cancel this out. So I have absolute value of 900 minus f equals e to the negative 0.170t plus natural log 500. But that is, actually I can probably fit it in here, but that is 500 times e to the negative 0.170t. How did I do that? Because e to the a plus b is the same as e to the a times e to the b, and e to the natural log 500 is just 500, and I moved it to the front. I'm going to take the absolute value bars off, so I have 900 minus f equals plus or minus 500 e to the negative 0.170t. And solving for f, I need to subtract 900 and divide by -1. So I get f equals 900, this is positive because I subtracted then divided, plus or minus 500 e to the negative 0.170t. All right, I do need to decide which of these I want. Okay, and because I need to satisfy the original condition, well, we could use either of these actually. Sure, let's use the easy one. 0, 400. If I plug 0 into this, 900 plus 500 does not give me 400, so I need to choose the subtraction. So f is equal to 900 minus 500 e to the negative 0.170t. Whew, that was a lot. Hopefully you're still with me. Okay, moving on to part B. This one's not going to be nearly as hard now that we have a function. So it says find the fish population in another 3 years. Why are you not scrolling? Oh, now you are. Okay, find the fish population in another 3 years. And we know that at 3 years, the population is 600, so it's asking at year 6. So this is going to be when t equals 6. So our fish is 900 minus 500 e to the negative 0.170 times 6. And again, I'm not typing 0.170. I'm using the value that was on my calculator, which is 900 minus, that comes, well, we'll just do the whole thing on the calculator. Okay, comes out to be about 720 fish. Okay, and then lastly, find the limit as t approaches infinity of f of t and explain what this answer means. So limit as t approaches infinity of f of t, let's write the equation. 900 minus 500 e to the negative 0.170 t. Raising something to the infinity, but it's a negative here, that's the same thing as the limit as t approaches infinity of 900 minus 500 over e to the positive 0.170 t. And if I plug infinity into that right here, I have 500 over infinity, which will approach 0. So 900 minus 0 equals 900. So what does that mean? That means that over time, my fish population will continue to increase, which is what it was doing. We started at 400 and then 600 and then 720, but my limit is 900 and I cannot go over that. So that means 900 is the capacity of the fish in the lake. It's as high as it gets. That's our interpretation.